In this question, we're focusing on the learning objective to explain projectile motion in terms of horizontal and vertical components. So the question, a cannon fires a cannonball with an initial speed v at an angle alpha to the horizontal. This equation is correct for the maximum height h reached. I was mentioning a moment ago that perhaps you could use the idea of units to just sort of eliminate some possibly incorrect answers. It probably wouldn't get you all the way to the correct answer, but let's take some time to maybe go down that rabbit hole. We want meters of height on this side. Will this give us meters on the right side? If not, we know it's wrong. Okay, if it does, it doesn't prove that it's right, but we could maybe eliminate some answers with this method. So this might not be like the best approach to solving like a multiple choice test on a time crunch. If you can just sort of think through it from sort of first principles and sort of arrive at some answer down here that you can then compare it to these and go, oh, that's the one that I think it is. So the units here of height are meters. The units of velocity are meters per second. The units of sine alpha are, well, there's nothing, right? That's just saying a piece of this angle, right? So like alpha is measured in degrees, but the sine of it is just some numbers, a ratio of sides. And so the units of g down here are meters per second squared. So meters per second are going to cancel meters per second, and there'd just be like a second left over in the denominator, which is actually, I guess, back up here in the numerator. So meters equals seconds. Nope. So we can eliminate choice A because the units just don't work. All right. Let's see about this one. Meters of height on the left. This is meters per second squared of acceleration due to gravity. Meters per second of velocity in the denominator, and it looks like meters per second are going to cancel, but then there's still a second like down here in the denominator. So do meters equal 1 over seconds? No, meters equal meters. So like B can't be right. So this is actually proven quite useful so far. All right, how about meters of height? We don't even know anything about projectile motion. We're just using units to solve this. Meters of height, over here we got meters per second. Oh, it's squared though, right? So we got meters squared per second squared over meters per second squared. So here, one of these meters per second squared cancels these, and we are left with meters. So like maybe, all right, it could be C. If we can eliminate G, we're done. We didn't even need to do any kind of projectile motion. We just use the idea of like base units, right? Let's see if it gets us there. So meters on this side, here we got G squared, so that's meters per second squared. That's just G. But if we square those units, then we actually get meters squared seconds to the fourth. This doesn't look good. Over meters per second of velocity. And so here, meters per second would cancel one of those. So we'd be left with like meters per second cubed, I think. And so that worked actually. The units are incorrect in all of them besides C. So C must be right because we can disprove the other three. Not the most efficient way to go about that, solution, but it works. It got us there. And so again, if you're like at a complete loss and you're like, oh, but I remember base units, and I got all the time in the world left to solve this one, maybe you could sort of rely on that thinking. Many paths to the same correct solution. Let's think about it in a different way. Let's go ahead and break this vector down and say, well, if it's launched at speed v, it's got an initial component of velocity in the y direction equal to v sine alpha. And then you can kind of see like v sine alpha, like that's kind of where these sine alphas are coming from, right? That's this component of initial velocity. You may recall that the height is related to, if we just drop something from here, this height would just be 1/2 gt squared, right? Like that's one way to think about sort of the height, is 1/2 gt squared. And we know at this point, the velocity goes to 0. So we can kind of think about this equation. The final velocity in the y direction equals the initial velocity in the y direction minus gt. So this is just equation 1, v equals u plus at in general, but because gravity is going this way, it's opposing this sort of positive value. So this term has to be negative. And then u sub y is this, v sine alpha. Remember the final velocity at this point, at h, the velocity in the y direction is 0. So we've got 0 equals, I'm going to substitute in this for u sub y, v sine alpha minus gt. Notice how there's no t's in any of these here, right? And so let's solve this for t. So we'll subtract this, negative v sine alpha equal to negative gt, dividing side by negative g. And we have t equal to, I'm just going to make these positive, v sine alpha over g. That's what t is, v sine alpha over g. Plug that in right here. H equals 1/2 v t squared, okay, is going to be v sine alpha squared over g squared. So I took that for t in the numerator and I squared it, but I put this back down here where it goes. So then this g will cancel one of those, and I'm left with h equals this in the numerator, v sine alpha squared over 2g. And that's that one then, right? So it works that way too. So you can just sort of think through your equations of motion, make some substitutions, a little bit of algebra, prove to yourself that h should be equal to that by actually sort of knowing the projectile motion. But these answers are so wrong that you can sort of disprove them just by considering the units. So many paths to the same solution. Either way you look at it, try to see. This has been a paper 1 worked example with Dr. Schleif. We'll see you next time.